going to say now is very important. This is part of the class I started about 3-4 months ago about stochastic processes and application to molecular and cellular biology. So today we are at the problem of escape from an attractor. So I want to go to a particular question and I will motivate it from neuroscience, where it comes from. So I think this is lecture number, I don't know, X is equal between 5 and 8, I forgot. So something between 8 and 9 and 11, let's say. So just to remind you what we discussed previously, we looked at the stochastic process. You have a stochastic equation, x dot equals b of x plus sigma of x w dot, which is the Brownian noise. This is the drift, deterministic drift. And let's say this is the tensor, diffusion tensor. And so what we have looked in the previous classes is the problem of escape, which is a classical escape problem since Kramer or even Arrhenius, but really Kramer 1940 discussed this question. You have the case where all trajectories of the deterministic dynamical system are attracted, let's say, to a point P, which means B here of P equals 0, let's call it P0. And P0 is an attractor. And here we have the normal outside. And on the limit cycle, we have, it's not the limit cycle, but on the boundary of the domain here, that we call omega, we have n dot b at each point P. This was negative. So all trajectories are coming and converging to that point. And now the questions that we have solved last week, I mean, it took us really 2 or 3 lectures, is to calculate what is the mean first passage time, starting from x, so the expectation of the time, where tau of x is the first time. That if you look at the trajectory and so we looked at the question when sigma of x could be written like 2 square root epsilon, where epsilon is a small parameter and no dependence on the position x. So tau of x is the first time that the first time t positive, that x of t is located on the boundary condition that, let's say, it started at position x at time 0. And now if you look, if you are interested in the mean first passage time, so we said that in the limit of small epsilon, asymptotically, there was a constant k epsilon, and we found the value of the psi here divided by epsilon, and psi was related to the minimum. So we looked at this when b was the gradient or minus the gradient of a potential, let's call it phi. So this is what we did last time. When b is the gradient of the potential, then psi was something like the minimum of phi on the boundary minus the minimum of phi inside. And the minimum of phi was here at the point P0, and then you have to look at the minimum, if there's any minimum. I mean, there is, but if there are several, it can be achieved at different points on the surface here of the boundary, on the boundary. Right, so this is what we found. We discussed this last time. So this is very, very well known. And now I want to look at the case where we have an attractor. And the question is, why do we want to do this? Now I would like to motivate this question by a problem in neuroscience that we started, we looked at a couple of years ago. And in particular, what happened when the attractor is not inside the domain, but it's located close enough to the boundary. And why is this important? We will see, because then the entire classical WKB approach to calculate this problem fails. doesn't work well. And now how do you study this? So in 2 hours that we have, I will not be able to do all the calculations. I'll present some calculation I will detail, and some I will present the general outline. All right, so now so this is to review what we did before. Now let's discuss about the motivation, which comes really from neuroscience, which is the distribution of what is called up and down state. So for this, so what are up and down state in neuronal network? So if you have an ensemble of neurons, so you have neurons that are connected, they form a network. So the big question, of course, that nobody knows, I mean, there are many questions in neuroscience that are unknown, but basically, what are an ensemble of neurons doing? It's unclear. It depends, of course, on the region of the brain where you are. But if you record, for example, continuously, you will see some activity, what is called spontaneous activity. And in particular, so this is like a neural network, very schematic. And if you record, this is now a time series recording. This is the voltage of a neuron. So you stick an electrode, and just I'm going to show you what you see from here. You can see what is called up and down state. That is, instead of having the membrane potential at minus 60 millivolts, you see some type of activity where the potential is spending some time as minus 40 millivolts, and then goes back to minus 60. And then there's this transients. And of course, what is the meaning of those transients? Why you can have something at the order of, let's say, 1 second to 2 seconds that have this depolarization? That depends on the network. If you can show that if, for example, you cut the connections, you don't have any more this type of activity. I mean, there are also intrinsic properties, but basically what we're saying here that this is a network property. Now, for understanding this, the first thing you would like to do is to have a model for having this kind of behavior. A model based on the analysis of the neuronal network. So about 10 years ago, a bit more, we proposed a model for a neuronal network that could produce this behavior of up and down state. So when you are at this state, this is called a down state, you are down, and this is called an up state. And so the models is based on the property that when two neurons connect, they connect, as we have heard in Jim's talk, Jim Rotman's talk 2 days ago, they connect by synapses. And at synapses, you have the release of a neurotransmitter from vesicles. And when the vesicle is released, and of course, if you have many action potential, that a succession of action potential, which happen when, for example, a neuron is firing, so a succession of action potential that should contribute to free the neurotransmitter. At some point, the number of vesicles that is there cannot follow anymore this ensemble of action potential. And this phenomenon is called depression. So depression is a physiological property by which the number of vesicles that you would like to release cannot anymore follow the rate of action potential. All right, so now the idea of the model of depression, so that you have a variable mu between 0 and 1, that will give you this, that will measure, that will account for this possibility to release vesicle. So this is the, you can think about it as the probability to release vesicle. All right, and so to build the model, you need to have another variable, which is either the voltage or the firing rate of the neuron. And here the idea is that you use a mean field model that is, instead, you can do a model for each neurons, but you can write also, if the ensemble is sufficiently connected, a parameter which is the voltage and this mu for the ensemble. And so I'll give straight away the equations that the depression model is. So you have for the voltage, there's a time constant to recover from equilibrium, which means that you recover like exponentially. This is what this term is. Plus a constant J, which accounts for the connectivity. Mu is a depression variable that I will write in a second. R of V is the conversion from voltage to firing rate, plus a noise term, which is sigma W dot. And so I will explain in a second all the terms here. Mu, this is the how this variable evolved. So if nothing happened, it should converge to 1 exponentially with a certain time scale TR. And U is a parameter. U is a constant. And R of V again is the conversion of voltage to firing rate. And here, I think I'm missing a mu. Yeah. So those are parameters, they are constants. J is, this is called the connectivity, the mean number of connectivity. This is the neuronal connectivity. And this is really just phenomenological model. Like Hodgkin-Huxley is a phenomenological model. So this is basically, this measures the noise. What is this noise exactly? How it is related to the physiology? This is not clear, but basically it accounts for all the noise that occurs, the noise of the synaptic noise, the voltage noise that is embedded in here. Right, and RV, the conversion, is just like V minus the threshold, the positive part of this, which means V plus is this. This is V plus, right? This is this when V is negative, this is 0, and otherwise it is V when V is positive. So when you have a large firing rate, the voltage evolves, so mu starts to, so here, if you wait for the system to evolve, when mu is going to, when you have a large firing rate, this is going to lead to a minus, so this will decay. So you start to be, the number of vesicles available is going to be depleted. And so it's going to be very hard for your system to feed back and to fire. So now I'll give you, again, this is the motivation for the mathematics we're doing today. You can ask, what is the phase space for this? What is the phase space? And what is the, how can this generate this behavior? So for this, again, I'm not going to show the detailed analysis of the phase space. So the phase space analysis is just by putting the noise to 0, and you can start to look at the critical point by putting V dot equals mu dot equals 0, and you just have to solve this equation. So the phase portrait, phase space. So let's call this equation 1. Turned out to be quite surprising. And again, for the phase portrait, this value of these parameters that I'm not giving here that are confined in table, when we found them, they were calculated from looking at physiological experiments. So they were coming with precise values. So this is 0, this is mu. So the phase space is mu and v. So this is going from 0 to 1. And so what we found is that there was a place that they are basically, depending on the value of j, you can have, there's a Hopf bifurcation for the critical parameter. So I'm showing you the phase space after you have the Hopf bifurcation, where you have basically a limit cycle. Here you have an attractor. So I'll discuss in a minute where it is located. You have here a saddle point, and it goes like this. And here you have another attractor, which is the resting state. And this is an unstable limit cycle, and it's depending, of course, on the parameters. So this comes, if you think about where this separatrix came from, it came from something that was, cycling around this limit cycle, and this is what you get. So this is the phase space. Again, one attractor, one saddle point, and another attractor. So let's call it A1, let's call it A2, and this is a saddle S. All right, so what happened?
Where is T? So this thing's going to...
What is T? Yeah, I'm sorry, the T here?
Yeah.
Yeah, T, let's fix it T to 0.
Okay.
This was just a threshold that comes from, but let's ignore it for a second. I mean, I'm not going to, it affects the picture, but I'm not going to discuss much here, the T here. Okay, so now, from this, what you can imagine, if you have now a noise, you had the noise in the system, then of course you can look at trajectories. So trajectories that start here in the neighborhood of the attractor can escape, and they can, once they are past this separatrix, they do a big loop and can come back to the attractor. Or when they do this big loop, they can enter into this region, which is the a limit cycle. So here you have a basin of attraction. And then when you fall into here, when you pass exactly the limit cycle, you fall into this attractor. So this region here corresponds exactly to this up state. Each time you are up, so obviously you're going to have some oscillation, which is predicted by this damped oscillation here. And now this is why we've been motivated by this question, and this is the class of today, is how long are you going to stay in this region? How long, and how can you calculate this? Once you leave this region, it turns out that this separatrix is very close to the, so again, I didn't invent this. We looked at it with the simulation. It's very close here to the limit cycle. So most likely when you reach this region and you can pass it, after some time you will also pass this, and then you will go back to this attractor without making any other loop. And those big loops are called, in neuroscience, this is like a population spike, that you go around this big region. All right, so now the question is, what can we say about the time of those events? The time the system is up. And what can we say about the distribution of this time? So this is the motivation. What can be said about the distribution of time in the up state? So again, we now have a model for this to start answering this question. So now, 10 years ago, we did some simulations, and I will show you now the result of the simulations. And then this is the motivation for redoing this analysis. When we looked, so this is the result of simulations. Of numerical simulation, you have your system, you just run many simulations, you look at the time in this up state, and what we found something like this. So this is the histogram, this is the time in the up state. Now the question was why? This is not what was predicted by the classical theory of escape from a limit cycle. So it took us about 10 years to go over all of this and to start understanding what is the meaning. Why you have picked. Okay, first of all, let's go back to the classical escape problem. What do we expect? So the classical escape, which is this question, if we look at the distribution of exit time, the distribution of exit time, let's call it P of t, is actually exponentially distributed, and tau here is exactly the mean first passage time what we calculated here. So this predicts that the escape time should be a single exponential. Now where that was coming from, for this we had to plot the phase space correctly. And it turned out from the parameter, and this is, so now I'll give you the right positioning of the phase space for the attractor, for the upstate. Metric, the distance do matter, not only the topology of the point where you can say that you have a focal point, but why the distance do matter, because it turned out that when we looked at it correctly, the cycle, the focus, which we called here A2, the focus was positioned very close to the attractor. Right? So then we understood what happened, and this is now the goal of this class, is to show mathematically that what we're going to describe now is mathematically consistent and correct, and how we can then from this calculate these peaks, where are they coming from in terms of the eigenvalues of the associated Fokker-Planck operator associated to the dynamical system. So this was the phase portrait. This was the unperturbed dynamical system. Everything was looping toward that point. And of course, when we had this trajectory perturbed by noise, you can imagine what happened. If this distance here was of the same order as epsilon, which is the size of the noise, since in this region there is no field, B is 0, this, we are in a region where the field is sufficiently strong, so the noise is small, but here the noise start to be significant, and then there's a certain probability that the trajectory escape. While if the trajectory do not escape, then it has to go around, and then of course we will be interested in calculating where what is the distribution of exit points. So what can happen? The trajectory goes around with almost a probability 1 and come back to this region where it can escape again. So then we can start to ask the mathematical question, is it true that basically the rotation here, which is associated to the imaginary part of the Jacobian when we linearize the field at that point, is this connected to the peak, the distance between the peak here that we have? And is it true that the distribution of exit point is concentrated in a small part here of the boundary and nothing around? So those are the questions. So this is the motivation of the analysis I would like to present today. So let me write the questions. And so why is this actually relevant in neuroscience? I mean, not that we understand where this is coming from. The idea is that pretty soon we are going to have continuous recordings of neurons in the brain. So, you know, there is no new technology to have a microscope embedded in the head of an animal, and you can record for hours. Now, how do you analyze continuous recording? What can you say about the local networks? So the idea is that, this is an example, if we have up and down state, if we plot this up and down state in here, if I have time I will show how to do, otherwise this is published. From the distance between the peak here, we can come back to some information about the mean number of connectivity. That is the mean number of connectivity. If you have an ensemble sufficiently connected that have this property, then the idea is that we could use the distribution of this event of up and down state, and from the mathematical analysis, if this model apply, because in general there are more than just the depression, there are more properties of synapses, but there are systems that are well characterized by depression only. Then the idea is that from this peak here, which I haven't shown you how to do, but you can basically extract the J. And why is that? Because actually what I said is correct. The rotation here, if you look at the matrix here, at the point where it is 0, if you linearize it, it's going to have it's going to be of order 1. It has eigenvalue and eigenfunction. The eigenvalues are going to have a real part and an imaginary part, which you can imagine that the imaginary part will depend here on this variable. And if the other are known, basically the idea is to recover from the distance between the peaks some information about connectivity. All right, so this is the motivation for today's mathematical analysis about this kind of question. So let me write the question that we'll be interested in. So first question, what is the distribution? What is the distribution of the exit point? That is when the trajectory exits, where is the distribution located? Is it located uniformly? The answer is, we will see no. As the point here is closer and closer to the boundary, the distribution is going to get picked at a point which is the minimum distance between the attractor here and the boundary. So what is the distribution of exit point? First question. Second question, we can ask what is the mean exit time? What is the mean first passage time? And the third question, which is not contained in this, would be if we have peaks here, what really we need to calculate is really the profile of the distribution of exit time. And this is contained in the entire, in the spectrum actually. So the first question, the third question is, can we compute the probability, the distribution of exit time? I call TE the exit time, probability that this is equal to T. And this requires to calculate the eigenvalues of the operator. So the first question, how to calculate, how to compute the spectrum of the Fokker-Planck operator. So why this is a non-trivial question? Because if you have a limit cycle, so maybe I should write the Fokker-Planck equation for this equation. So the Fokker-Planck equation is the probability distribution function of the couple V and mu. So the Fokker-Planck equation is a solution of dp dt equals, so in general, if we have a dynamical system which is x dot equals b of x plus square root 2 epsilon w dot, this is epsilon Laplace np minus the divergence of b multiplied by p. And so there is, and we have the boundary condition is p equals 0 if you're on the domain omega. So this is the equation on the domain, and we have here the absorbing boundary condition on the omega. And the distribution of exit time is usually the integral over omega, and if you differentiate this divided by time, this is exactly this probability that the time equals t. So this is what we have. Basically, if you ddt, this is the divergence of the flux, so this gives you exactly the flux here. So why this is not trivial? Because in this case, B, when you have a limit cycle, cannot be a gradient. And if it cannot be a gradient, what do you find? So if you have a gradient, basically you can always transform the question of finding the eigenvalues as a minimization problem. You minimize the quantity for the first, the second. But if you don't have a variational formulation, we have to, you cannot use all of this technology. So again, it took us a couple of years to understand where and how to find the eigenvalues of a non-self-adjoint operator. This operator, when we'll have this, because of the limit cycle, cannot be put into a variational form because B will never be a gradient of any function. And so the problem, if you look in the literature about the problem of finding the spectrum, it's mostly open. The spectrum of a non-self-adjoint operator. So how to compute the spectrum of the Fokker-Planck operator, which is really non-self-adjoint? All right, so this is the motivation. And now what we need is to analyze the equation. Basically, let me remind you the important equations for each of the questions we have asked. So the distribution of exit point, you remember we looked at this in the class, it was maybe class number 2 or 3. We have an equation for the distribution of exit point. That is, if we solve this equation, we answer this question. And so let's now write what are the partial differential equations that are needed to answer the different questions here. So for the question number 1, the distribution of exit point, what is the operator? I think we had them on the first class, right? Or second class. This was, so if we wrote this as an operator, let's say L of P, this is the L of P is this operator as a function of P. So L of P, or L star of P, what was in the note? This is L star means the adjoint with respect to the L2 integral. So this was equal to 0 on omega. And we had to have like a condition like P of x on the boundary equals delta of x minus y. And this, the interpretation of this was P was the probability that the density probability that a particle escape exactly at point y. Right, so this is the classical calculation. So if we know how to solve this, then we could have an information about the distribution of exit point. For the mean first passage time, I want to show that we have a family of equations, and the solution is going to be basically what is called WKB form. And then we can use WKB to look at the different asymptotic solutions. So for the mean first passage time, the equation is L star. So L star, so let me write it L star once. This is epsilon Laplacian P plus B. So this is self-adjoint, and then you have to integrate by parts to get this term, which is B gradient P equal minus 1. And P, let's call it U. And U equal 0 on the boundary of the domain. So if we know how to solve this, U of x will give us the first passage time condition that the particle started at position x. So U of x is exactly the mean first passage time condition that the particle started at position x. All right. Now, so we have mean first passage time, distribution of exit point. To get this distribution of exit time, then we need basically to solve the entire Fokker-Planck equation, the time-dependent Fokker-Planck. And formally, what is this? What is the solution formally? The solution we can always expand in this in the basis, assuming that we know a base for this solution. So let's suppose that at time 0 we have P x t condition of y. P, I suppose that you start at position y at time 0, which means this is a delta Dirac at x minus y. So P formally what we get is that p x t conditional y. So we know that the first, so if we have a positive non-self-adjoint operator, we know that the first eigenvalue is going to be real and of dimension 1. So we can write it this way, exponential minus lambda 0 t. And then we have u0 of x, v0 of y, plus sum of n and m, exponential lambda n m. And so this is t, and this is u n m of x, v n m of y. So the u n m are the eigenfunction of L, and the other one, v and m, they are the eigenfunction of L star. Okay, in principle here, the eigenvalue are not real, but so this is real because the first one, as I told you, is real, and this is of dimension 1. So what we have in here is, I take the real part of this. And here, of course, no, this is what you get. Yeah, V can be something of this type, which is the conjugate value for V. So in principle, it's not enough to, so what is lambda 0? Lambda 0, this is the first eigenvalue. And the first eigenvalue, so those are the classical properties. Lambda 0, so lambda and m are the eigenvalues. And it turns out that lambda 0 is real. So if this is real, this means that if we integrate this with respect to x, and we can differentiate to get this probability of exit time, this will give us something that can only decay. So we should not expect any information about the oscillation coming from this, because this is decaying. However, those terms here, that's are not real. They have an imaginary part. This is what we are interested in calculating. So we are not interested in calculating the first eigenvalue, which is actually 1 over the mean first passage time. So it can be shown that this is 1 over tau, the mean. We're interested in calculating the other one. So how to calculate, how to compute the lambda and m. All right, so let's continue 5 more minutes and then we'll break, and then we'll continue after the break. So how to calculate the lambda and m, which are obviously solution of the eigenvalue, eigenfunction, which is here for u, it's L, u and m, equals minus lambda and m, u and m. This is the this is the eigenvalue problem. Okay, so at the beginning we saw that this was a difficult question, so we wanted to have a model for this, a general model that we've used. So let me give you this model, and then I will write this down to have a generic dynamical system where the critical point can be arbitrarily close to the boundary. How do you build it? How do you find it? And then I want to spend time using WKB. So WKB is a certain form to a certain form for the solution, U and P. And I would like to use this to show you how you can calculate where the equation for the eigenvalues are coming from. It turned out that it came as a surprise. This equation is hidden in what is called the boundary layer. This is an equation that actually lives in the neighborhood of the limit cycle. That we have missed, us and many people, for many years, because it was hidden in here. And by resolving this in what happened in this boundary layer, you can find explicitly an explicit expression of this eigenvalue as a function of the property of the vector field along the limit cycle. So before doing this, let me show you that we present to you the generic model. So this is simply actually using the classical Hopf and using a Mobius transformation to map the attractor as close as we want to the boundary. So generic dynamical system with a critical point as close as we want to the boundary. So let me remind you what is the classical Hopf. The classical Hopf system for a dynamical system in dimension 2, which is z dot equals d of z, that has a limit cycle and a focal point, can be written as the form lambda z minus 1 plus z squared plus I omega, where lambda and w, let's say, are real non-zero values. Right, so you can see that z equals 0 is a critical point. This is 0. And then z equals 1. This is a limit cycle, right? If you have z equals I theta, you can even calculate along, so you put that in here, and you find an equation. So z dot is I theta multiplied by theta dot. This is 0, so this is lambda I theta, I omega. So this goes away, and you can have exactly the speed along the limit cycle, which is lambda omega. Right, so now how do you transform, how do you build a dynamical system where the critical point is as close as you want to the boundary? Basically, you don't want to destroy the limit cycle, and you want to move this close to here. That's it. So for this, you use the Mobius transformation. So this is, let's call it eta is phi alpha of z, where alpha is going to be a parameter minus alpha z. And so what you have to do is you have to conjugate this vector field with this Mobius transformation. So you get your new dynamical system, which is C dot equals B alpha of eta, which is phi prime phi alpha minus 1 eta, B0 of phi alpha minus 1 . And you can even plug, you can do the calculation, you invert this, you put that in here. So this basically will send this z equals 0 is said of something which is minus alpha. And so when alpha is as close as you want to minus 1, this will converge to a point here on the boundary. All right, you can even do the again, I'm not going to do the calculation, but basically you can get this. This is lambda psi eta plus alpha 1 plus alpha eta divided by 1 minus alpha squared minus 1 plus eta plus alpha 1 plus alpha eta squared plus I omega. Now you have a dynamical system, and now we can make a perturbation of this dynamical system, which is x dot equals b alpha eta plus square root 2 epsilon w dot. And now the idea of having something explicit is that we could do explicit calculation. All right, so I'll break here, let's say 5-10 minutes, and then we'll resume by looking at the solution, how we do the solution of this equation. And so when I will refer to the system here, I will refer to this explicit calculation, because again, the idea here is we know exactly how things are going, what is the power of alpha we want. I mean, so this is important for the calculation that we're going to do. Okay, let's break. I should stop recording, right? That's it. Okay, what I was saying. Yes. So to the idea that why we can expect to answer this question is that because this point is going to be close enough, we'll have sufficiently concentrated, let's say, distribution, and then we can have a profile that as the distance here goes to the limit cycle, we expect the escape to be located in a small neighborhood here. And of course, there is no intuition about how to get the eigenvalues. So for this, let's go step by step. So let's discuss what is the asymptotic approximation of this equation. So for example, if we have for the distribution of exit points, this is more or less the same operator, either itself or the adjoint, L or L star, I will discuss. So let's talk about LP, which is epsilon Laplacian P minus divergence of B gradient P. And for example, this is equal to 0 or to -1 or to a distribution F. So this is our function F. And then we need an important condition, which is P equals 0. And the problem is to build a solution of this equation that will satisfy this. And this is where we need what is called matching boundary condition. That is, usually a solution of this will not necessarily satisfy P equals 0 on the boundary. So this we have to do something. And this is called boundary layer analysis. How to find the solution of this, which is also satisfying this. Okay, so the general methods to approximate the solution of this is called WKB approximation, which is well known, has been used. So we'll talk about, we'll discuss it, I think, 2 classes ago, like 1 month ago before the break. And it is well known in quantum mechanics, is to look for a solution of the type P, let's call it P of y, equals K epsilon. So this is the same epsilon that is here, multiplied by exponential of minus psi divided by epsilon and psi of y. So the idea is to split the solution of something which is exponentially small to account for this term here. And psi and k as we're going to see, have to satisfy some condition and some equations. Right, so this is called the WKB approximation. And now, let me write something here more specific. K epsilon of y, if we can expand using a regular expansion in epsilon, can be expanded like K0 of y plus epsilon K1 of y plus something like this, plus a series that will going to be quadratic and cubic in epsilon, multiplied by a boundary layer term, which is the solution, which is the solution that will be able to match this p equals 0. Q epsilon y has to be equal to 0 for y on the boundary, and in the limit epsilon goes to 0, Q epsilon of y equals to 1 for any point 1 inside the domain. It's basically something that goes to 0 and has to match. This is so this is 0, this is the domain, this is the boundary of the domain, the omega, and this is something that we will see that allows us to match 0 from whatever positive solution. Yeah, everything mean first passage time is positive. We are talking about positive quantities. All right, so now if we simply take this and plug it into in here and look at the terms, so for example, this equal -1 or 0 or f, function f is independent of epsilon, then we are going to get an equation that will contain terms in epsilon at different orders. All right, so again, there is a calculation here to be done. Just let's take this and plug it into here, calculate the second Laplacian, then the divergence of B gradient P. And because we have epsilon in here, and we have the term here which is of order 0 in epsilon, we'll have an equation both for psi and k epsilon. So, I mean, have you ever done this kind of calculations? No, it's not very hard, right? I don't want to do all of this, but basically, you know, gradient P is going to be gradient K exponential minus C divided by epsilon plus minus gradient psi divided by epsilon multiplied by K exponential minus psi divided by epsilon. And then we can calculate the divergence of this, which is divergence of gradient P. So again, it's going to be the divergence of K exponential minus epsilon psi divided by epsilon. Divergence of this is going to be the minus the gradient K gradient psi divided by epsilon exponential minus psi divided by epsilon. Here we have minus Laplacian psi divided by epsilon, K exponential minus psi divided by epsilon, minus gradient psi multiplied by gradient K divided by epsilon exponential minus psi divided by epsilon, and then minus gradient psi squared divided by epsilon squared, K exponential minus psi divided by epsilon. Okay, and then I'll let you do this term here, and we'll multiply everything here by it. So now we'll have to multiply the Laplacian by epsilon, so we'll get an epsilon here, this will go away, this will go away, this will go away, this is now divided by epsilon. And then what we need then to calculate, we have gradient P. Now there is no gradient P here, right? It's B. Oh, this is, yeah, depending what we want to calculate. if this is the adjoint or the self-adjoint operator, it's divergence of BP. Okay, anyhow, this can be written like, so for calculating this term, this is going to be B multiplied by gradient P minus divergence of B multiplied by P. So I'll let you finish the calculation. And so what you get, now we have terms in 1 over epsilon here. So there's a term that is of order 1 over epsilon, where this term can be counterbalanced. So again, so if we have to add minus, so this is divergence B multiplied by P minus B gradient P. So minus B gradient P, so I have to multiply this by B, right? To have this plus this plus this. So this plus the 3 terms is going to be equal to 0. So basically to get this term here, I have to multiply this by B, which is gradient P multiplied by B, exponential minus psi divided by epsilon minus gradient psi multiplied by B divided by epsilon, K exponential minus psi divided by epsilon. Correct? And then I have a term here. So this equal to 0. I just show you the first order term. So this is of the order of 1 over epsilon, and this is of the order of 1 over epsilon. So in order for this to not blow up as epsilon goes to 0, this plus this has to be equal to 0, right? And so this is called the Ecole equation. Which means, so this is gradient psi, right? Because k, this will go away, k and k, plus b gradient psi equals 0. So this is a first order nonlinear partial differential equation. And now you could do the same just for looking at the term of order 1, and you get what is called the transport equation, which actually can even contain terms of epsilon. So let me write down what you get when you remove this term. You get epsilon Laplacian k minus 2 sum of I deep C I dx I plus d, the vector field, dk, this is really the scalar product of this multiplied by this. Basically, this is coming from the term that you have in here, gradient k, gradient psi, and then there should be a b that will come from here. So you have to, this is going to be summed here, dp dy, minus, and so this is a divergence term which I'm writing in the coordinate system. This is dpi dxi plus a term which is over j, which is d psi dy dyi plus 2 d psi dyi. So this is sum of I, and all of this all of this is multiplied by k. Everything here is multiplied by k equal to 0. And this is called the transport equation. So again, at home, you just go and do the calculation. It's very it's elementary calculation. This first order term I did, you just look at the term that is blowing up in 1 over epsilon. In order not to blow up, it has to be equal to 0, and that's why you get this, and the rest will give you this transport equation. Okay, which means that if we want now to solve this equation, we need to find out psi, and we need to find out this k epsilon. So we have basically two equations, with for these two unknown. So now, of course, the difficulty, okay, is how do you find a solution for this and a solution for that? So once you have a solution for psi, you know it, so you can use it here. So p is known, psi is known, and then you have like a partial differential equation for k. And you will see that this can be simplified. We can neglect here this term of epsilon, and thus we end up with an equation that is of first order k, that can be solved, what is called the long characteristic. So let me now discuss the solution, or what is called the solution of the Ecole equation. How do we solve the first one? And once we have the first one, we will go to the next one. Okay, in general, this is a hard equation to solve, especially if we are in abstract domain. So the way to solve the Ecole equation is through what is called the characteristic methods. Have you ever heard about what is the the method of characteristics? Yeah, how do we solve in general an equation of like f, x, let's say, let's call it psi, and we have d psi, dx, dx1, dx2, whatever, the first derivative, second derivative. This equals 0. So in here, this would be, so this equation will be here, so let's call it, let's rewrite it x, psi, and p, and this is be like p squared. The gradient psi is basically the variable p. This is like a vector. So this is like p squared plus b that can be a function of x, where we are, scalar product p. Right? So how do we solve, for example, this equals 0? So we have to construct what is called characteristics, which are the solution of, it's usually in dimension, if the system is in dimension n, we're in dimension 2n plus 1, and which is usually x dot equals the gradient of p of f, p dot equals minus the gradient of x of s plus df psi, and then the c dot equals p gradient for the variable p of f. So if you are, for example, in dimension 2, this is already dimension, how many? So this is, if you're in dimension 2, which means you have x, x1 and x2, so we have two equations. Here we have two equations, because we have p1 and p2. And here we have one, so we have already 5 equations. So it's very non-intuitive to understand this. I mean, you have really to go numerically and to solve this equation in general. So what do we have here? So f is a quadratic form in p. So this is what? This is simply 2p plus b of x, right, to differentiate with respect to p. This is simply minus, this is gradient b multiplied by p, and this is 2p squared plus b p, but since this is 0, we are left, there's 2p, so I get 1 out, plus this p squared plus this equals 0, you are left only with 1 p. All right, so this is the general equations that, and if you are along the characteristic, you know that the solution is constant. This is basically what you get. So if you have a solution of this, and you write df, so if now you call x, p, and psi of t a solution, xt, pt, and psi of t is a solution. So basically you have a dynamical system, you have an initial condition, and you know, can calculate the trajectory. So this is deterministic. So what do you have? You have that along the characteristics. So f, if you differentiate this, I mean, this is, so you have d of f of psi of t and p of t, this is equal to 0. Okay, so now this is a general approach, but of course we can say more. For example, we need basically what is important is to understand this solution close to the limit cycle, in the case that we are studying here, and close to the critical point. Now it turns out that you can solve, we can understand what is this equation near a critical point just by looking at it. What happened at the critical point where b is 0? If b is 0, this term is 0, right? So then we have gradient of psi, which is 0, because this is 0. So which means that psi should be a quadratic function near x equals 0. So again, at the point where b is 0, this is 0. So which means that the norm of the gradient is 0. So this is a critical point for psi. So psi, if it has a regular expression, which you can show, should be quadratic form at 0, at the critical point of b. So properties of psi, solution of the Ecole equation. All right, so near 0, let's call it, let's say near the point P, or P alpha, where this is 0, necessarily we have gradient psi at this point, which is 0. So psi can be written, so let me now suppose that the origin 0 is the point P alpha. Now I can get a system of coordinates, x1, x2, or xy, and write it this way. This is 1/2 of transpose x. X is, let's say, if you're in dimension 2, this is a vector coordinate system near at 0. And this can be written transpose x, qx. Now, if we use this and plug it in here, what do we get? B of x, so near 0. What is B of x? B of x has a 0, so it can be, let's write it a matrix A multiplied by x, right? Plus small o of x, because it is 0 by definition. Now we plug this into this equation. What do we get? So it's not hard. We have to differentiate psi with respect to x. So this will give us q of x. So gradient psi squared is going to give us q of x, right? And I'm looking here for a symmetric matrix. So I don't know what is Q. Q is unknown. Unknown. And I take it as a symmetric matrix. So I have something like this. And I have to write this B gradient psi, which is what? Which is at least at first order, is going to be A of x and gradient psi, so Q of x, and I want to symmetrize this so that it will satisfy, I will get a symmetric equation to satisfy. So let me write it, this is 1/2 of A x qx plus the same thing, ax qx, and now I'm going to use the transpose of the matrix. So this is going to give us 1/2. So let's write it, let's take A in here. So this is x transpose aq of x plus, and now let's do it the opposite. So this is going to be, let's put the q in here. So we'll have transpose q, but q is symmetric. So transpose is not changed. So this is x, x. So this plus this, by definition, should be equal to 0. So what do we get? This is true for all x. So what do we get? We get 2 multiplied by this, qa plus transposed a, q, no, q plus this equals 0, right? And this, so this is q squared. And so this is called the Riccati equation. If you have ever seen that. This is the classical Riccati equation. And again, you can solve it using an integral. I'm not going to, I'll give you the steps, the different steps. So this is well known. This is called the Riccati equation. This is well known in control theory. It's very important over there. I mean, so it comes exactly here again. So this is important because, you see, we relate by Q the property of B through the linearization at the critical point. All right, so I'm not, okay, now we have to solve it. It's possible to solve. There is a formula, I haven't written it. I think Q should be like the integral from 0 to infinity of A plus A transpose exponential something. It's well known. I don't know, I don't remember. It's unimportant at this stage. What is important is this, this can be done this way. All right, so now we have some property of psi at the critical point. And now let's find the property of psi near the limit cycle. Right now I leave this, and this is true locally. So this is, now we have an expression for Q locally. And of course, psi here is defined up to a constant, right? If you add a constant, it drop and it drops. So it's clear, it's defined up to a constant, and this is for x local. Okay, now if we are interested in the property of psi near the limit cycle, we need to have some assumption about the field. What is the field close to a limit cycle? Now it's not clear, there are many possibilities, but let's choose the generic one. So now this is about the properties of psi near the limit cycle. Okay, so what do we know about the field? That the limit cycle is a limit cycle. What does that mean? It means that B, so the solution of this system, the x tilde, which is the periodic solution, should be solution of this equation. But now if we go in detail into an expansion of B close to the limit cycle, what is the generic form of B? So B of x has a normal, component here, and a tangential component. Let's call it T and N. So what can we say about those two components? Basically, as we get closer to the limit cycle, the normal component should vanish because we have only the tangential component because it's a limit cycle. So we can always write it this way. This is B0. So now, if it vanishes, of course, we can always decide at which degree it vanishes. So it's going to be a function of S. S is the arc length here. So let's assume that it vanishes, and rho is the distance to the boundary. So the distance of the point P to the boundary. It vanishes to order 1, multiplied by the normal. So x is variable rho and s. Rho is the distance, and s, let's say you can think about s as the angle. And then we assume that there is a component which is a tangential component. That is when you are exactly starting on this limit cycle, you stay on the limit cycle. So this is a tangential part. And we're going to make some assumption that B of S has no zero. That is, on the limit cycle, the field doesn't vanish. So for example, let's fix a positive or negative sign. Let's say positive. And B of S, B0 of S, it's again a function that we can assume that is also positive. Okay, so now let's look at this equation on the limit cycle and see what we can say about psi. So on the limit cycle, B has only, if you start only on the limit cycle, B is only tangential. It's only tangential. So this is the scalar product, so you can only take the tangential part, which is this B of S. So let's rewrite this equation. So this is gradient psi plus B. So B, again, if you are exactly on the limit cycle, rho is 0, right? So we can always write it B0 as rho normal. This is a normal component. So then we have, let's say, deep C dr plus deep psi ds multiplied by this B of S. And now if we are on the limit cycle, since rho equals 0, this is 0. And now, clearly, what does it mean? So suppose if, for example, B of S equals 1, just for simplicity here, and you integrate this over the limit cycle, what do you get? Integral of this plus integral of deep psi ds, but once you go around, since it has to be periodic function, this is 0, So this is exactly 0 on the entire cycle. So if this is 0, again, what does it say about the expansion of psi? It's, let's say, a constant, plus a term of order 1, which is 0, plus a term of order 2. So what do we have in the end? We have that psi rho of S along the limit cycle is a constant psi that is plus 1/2 of rho squared phi of S. Right? So there is no term of order 1, and you do an expansion in rho. So the first term is 0. And then you have this system, and then there's a function phi of S. Okay. So for example, if we take this and plug into here, and plug into this yeah, okay, now this is what we have. And so then plus rho of rho squared. And of course, this is an unknown function. We have to find out how to get this function phi of S. So phi of S is a function to be determined. Okay, so now at this stage we have we have some properties, some local property and some properties of psi along the limit cycle. And now to continue to get more information, as I showed you here, the psi and k are connected in here. Now what we need is to actually look at the transport equation. Okay, so now let's discuss this equation. So now we are entering into something important, because this is in this equation that we will find out the information about the eigenvalues of the problem. Okay, so now we can write this equation near the limit cycle using this this local approximation for the field, which has the normal and the tangential component. Okay, so for example, this is just gradient k multiplied by b multiplied by gradient psi. But gradient psi, we just said near the boundary, that is going to be 0. So now we can rewrite this term and this term here, and I'll go to the case here where in here this term here is negligible. That is, this is of order 1, and in the limit epsilon goes to 0, I don't care about this term. Condition that this, of course, doesn't blow up, but actually it doesn't. And so we can rewrite 2 gradient psi plus b here. This is going to be rewritten as rho 2 phi of s multiplied by n, and then there is a b of s n. So along the limit cycle, so this entire term here, So this can be written in the form b of s dk0 ds plus b0 plus phi of s plus b of s. So I'm skipping here some calculation. It's just like a Taylor expansion of this in the neighborhood of the field. But basically, this is, what is the philosophy? This is of order 1. And along the limit cycle, this is just dk ds. This is a term, whatever it is, multiplied by k. So this is basically a first order equation. So this, of this term, dk ds b of s, plus a term here, multiplied by k, equals 0. And this has to be periodic. This equation has to be periodic. When you go back here, you want to find. So this is an equation for k0. Okay. So now this is when we are on the limit cycle itself. To get an information about what happened not on the limit cycle, but in the neighborhood of the limit cycle, we are going to go back to this equation, because this can be written this way. So this is about, again, this is about what happened on the s direction. Now I want to see what happened perpendicular on the rho direction, on this distance. Because now what we need is to find an equation for the boundary layer, for the connections. So for this, what you need is to scale the variable. So you have q epsilon of x, and we are going to introduce a new function k, and k is just for scaling with a variable eta, a rho divided by square root epsilon. So this is of x, and now we have something of eta. S is the abscissa variable, and we can write it as depends also on epsilon. Now, when you take this, and now we plug it in k, and now we look at an expansion for q, but not anymore just on the cycle, but we need the other variable which are perpendicular, and this is where things, where we start to have the equation for the boundary layer. This is d, so again, basically, when you have this square root of epsilon, when you differentiate twice, the epsilon got inside. So that's why the term here will correspond to the term that is perpendicular, which is parallel to rho. So this is eta squared q0 minus eta a0. This is b0 of s plus 2 phi of s dq0 xi minus b of s. Again, I'm not showing all the detail of the calculation. This is dq ds, and this has to be equal to 0. And now we have the condition that q0 of s at 0, this has to satisfy this, has to be equal to 0. And far away, inside the domain, q0 of psi, whatever position s, and psi goes to minus infinity, which is when you go back to the domain, this has to be equal to 1. Okay. So This is a very important equation because this is the term that gives us the boundary layer. It's also the term when we have this proportional here to lambda q0 that will give us the spectrum. So but let me now finish with this q0, which is this term here. It turns out that this can be, we can integrate this, and there is a trick for this. You see, it's if this was independent of S, you have something of psi squared, psi, and if this was independent of S, it's like when we do separation of variable. That is, this is psi and this is of S. So you look for a solution which is as with separate variable. Now the question is how you get rid of this. We have to find a trick to put this away in here so that this is becoming independent of S. And this is possible by using the Bernoulli equation, which I have forgotten to write. I'll find it in a second. So now the idea is that, remember, the phi of S here was, I left it to be determined. Now we are going to use it here to separate the variables. So let's take phi squared plus b0s phi plus 1/2 of b of s phi prime equals 0. So this is called the Bernoulli equation. So I'm looking for phi. B and B0 are the data of the field. This is how the field is along the limit cycle. So this is known. So if this and this is known, can we find a periodic solution to this equation? The answer is yes. This is the well-known Bernoulli equation. You can find an explicit solution by transforming it back to Riccati. I forgot how. I think we have to. Yeah, I see. You have to divide this by phi squared. You can transform this into a linear equation by using phi prime divided by phi squared and write this as like 1 over, let's say, psi. Oh no, let's do psi equals 1 over phi. So psi prime, yeah, it's minus phi prime divided by phi squared. Right? So you see that if you divide everything by phi squared, you get psi prime here, and this is becoming 1 divided by phi, which is psi. And now you can solve it. Why we did all of this?
Because you were choosing your phi in such a way that you can.
Yeah. So that this now I want to show you the magic how this disappeared. Yeah, okay. So now, if you multiply everything here by phi squared, what do you get? You get phi squared, 2 phi squared, which is this one, plus B0. So let me show we have want to make sure I haven't made any mistake here. Yeah, okay. So this 2, 5, yeah, this is correct. And now, yeah, okay, now there's another trick. We have to change variable. Okay, so now what you do is, this is Q0 of psi and S. And now what we need, and it's not written, didn't print correctly, so now we need to change variable to introduce a function, let's call it Q tilde, of a function of S. So this is, I think it's phi of S, psi S. Okay, so I think this is correct. So now when you plug this, now you have to, we have to write an equation for Q tilde, so I'm sorry, Q tilde of S, this is Q0 phi of S, psi S. All right, so now I'm looking for a solution, I'm looking for an equation for Q tilde, where this is this solution, but now I have to, I have introduced here phi of S eta, psi. And now what we need to do is to differentiate this with respect to S and psi, find a partial differential equation for this. And it turned out, so I'm not showing it here now, but because of this, what we get is that d dq d eta, so eta is a new variable which is this, plus eta d dq d eta minus b of s divided by psi of s. So this is a solution of another Bernoulli equation, which I will another Bernoulli equation, and this dq ds equals 0. So what is nice now is that this is with a separated variable, that you have everything here in S and everything here in eta. And psi is the solution again of a Bernoulli yeah, this is solution of minus psi cube plus b0 of s, psi of s, plus b of s, psi prime equals 0. Not exactly, this is a different Bernoulli equation for psi. And finally, with this, you can look for a solution. So this is with a separated variable. You can think about this equal to 0, and you get for q, you get q of psi and s which is minus 2 divided by pi, integral of 0 of psi of s eta exponential minus z squared divided by 2 dz. And this, now if we go back to the first, the general solution, u0 of y is exponential minus psi of y divided by epsilon, k0 of y multiplied by this q epsilon, which is given by this solution of this, which is 2 square root epsilon. You have to integrate from 0 to minus the distance to the boundary. Eta of s of y. S is the, when we go around the circle, this is the curving axis. S of y divided by square root epsilon exponential minus z squared dz. So in principle, psi is solution of the conal. K0 is solution of the transport equation where we have given some characteristics. And this, so this give us the general structure of the solution. Now from this, we can calculate, for example, the flux. I mean, there was 4 questions that we discussed. For example, how do we calculate from this the distribution of exit point? The distribution of exit point corresponds to the flux. So this is a generic solution of this equation. We need to calculate the flux, which means the derivative of u with respect to the normal, and take a point psi on the boundary. That's why we calculated informations for things, for example, for psi on the boundary. Yeah, I'll do this, and after maybe we'll have the time to finish everything today. But let's start now to look at the properties. So now if you want to calculate the distribution of exit point. The distribution of exit point are given by the flux j dot n, that and the probability to exit at a certain point on the boundary is this normalized. So we have to normalize this over the boundary. So this is the probability. So for example, if we have, this is the probability that, let's say, the point exit at position y. So this is the flux at y, and this we integrate, for example, y ds, it's like x, the point x, ds x. Now how do we calculate the flux? The flux is du0 dn at rho equals 0 on the boundary. So now we said that, so this is basically there is one function, 2 functions, 3 functions. So gradient u is this, which is exponential multiplied by this gradient psi. But we said that psi on the boundary, if you remember, was 0, that there was no first order term. So this will give no contribution. The gradient k also will give no contribution. And now what we need for this calculation is to differentiate this term here with respect to the distance which is linear in the distance, because this is integral from 0 to the distance. So when we differentiate this and we take rho equals 0, this will give us 1, and then we'll have to get, we'll get this, this term in the derivative. So we'll get this will give us exponential psi at the boundary, so we call it psi tilde in here, divided by epsilon. Then we have k0 at the point S because we are not just looking at what happened on the boundary. There is this 2 pi, and then when we differentiate, there is this term. So distance will give us, so we have to differentiate this, so this is square root epsilon, and then psi of S. And also here when we calculate the flux, the flux, I'm sorry, this is not exactly equal to this. This is, the flux is epsilon gradient rho minus b p. This is the flux. So this is epsilon dp dn minus b dot normal multiplied by p. But b dot normal by definition, this is 0. So here there is an epsilon because of there. So this is correct, except that I have to multiply everything by epsilon. But since I have an epsilon here, I just have to multiply the epsilon here. And then I take this, put it here, normalize, and now I have the distribution of exit point. Distribution of exit point depends on the solution k0 of S, which is this solution that we have found that depends on the solution of Bernoulli plus some property of B. Psi of S, I think I wrote it, yeah, this is the solution of another Bernoulli equation. So basically, now we have this. Why I wanted to show you all of this, because I'm not sure this is ever shown, all the details of how you solve the escape problem with a limit cycle, and this involves all of these steps. But now let me show you what we get when we plug yeah, okay. You remember, so Kevin asked about this conjugated dynamical system. Now, so I'll present for next time. You can calculate everything for this dynamical system. You can calculate this and this. Everything can be calculated. I'm not showing that now, but I'm going to show you what it gives, the results. So you remember there was this parameter alpha. So it's 1 divided by 1 plus 2 alpha cosine theta plus alpha squared divided by cube, and this is normalized. Now you have to take the same thing and you integrate between minus pi and pi this theta. 1 plus 2 alpha cosine theta plus alpha squared cubed. So this is the probability to escape here. I should write really the probability to escape, that the escape point is at theta, where theta is the angle. When you have this circle, you have this point, which is here at critical point at position alpha. And now you can see exactly what happened. What happened when alpha converges to -1? You get exactly what is called a blow-up. That is, this is a measure that exists on the circle that will be picked here exactly at theta equals pi. Theta equals pi, you have cosine equal -1, and you can see that for at -1, when you get 1 minus alpha squared, and when alpha goes to 1, it goes to infinity. So this shows that for this, you get exactly a measure that will blow up. So most likely the probability of exit point is in here. And I have to admit that we had a fight for about 5 years with people claiming that the distribution as epsilon goes to 0, the distribution were oscillating. So we never saw this. We saw that this is what the theory predicts, and if you do a simulation, you don't see that it goes. So this says that the maximum is exactly for theta equals pi. But there is here actually a difference that you can see in the simulation of the order square root epsilon. That's the maximum here, and so this is much harder to find why it's at square root epsilon. But this is called skewing. It has been discovered numerically in 1982. That the escape, the maximum of the escape, is not yet theta equals pi, but it's at a place of a distance square root epsilon. Okay, so this again, I haven't shown all the detail of the calculations. Now for the people interested, you can go into the calculation, but what is important is the different steps. So this is, we have solved one of the 4 questions. I want to stop here because it's 5 o'clock. Next time, I want to show what is the mean first passage time and how the mean first passage time depends on alpha. And maybe I will write this and now and discuss also next time how from this equation, which is written here, I mean the equation that was written before this one, where the spectrum is coming from, why the spectrum is hidden in a boundary layer of the limit cycle, and how from solving it we can get explicitly the eigenvalues as the properties of the field, which is how the field behaves near the limit cycle. But so before closing, I'll give you the results. For and now this is what we'll do next week. The mean first passage time turned out to be exponential psi divided by epsilon, and then there was a constant here. Whatever the constant is, it's unimportant. But now we needed to calculate. So for example, you can fix, as I told you, the Ecole equation, you can fix a constant. So you can fix, for example, at 0, at the critical point it is 0. But then if you fix this, how do you calculate the value of psi at the boundary? Now this is in general impossible. You have to go through the solution as I show you along the characteristics. However, if this point alpha is close enough to the boundary, you remember we said that psi is quadratic near this point. So if it's quadratic and if this is close enough, we can use the quadratic expansion because it's just a Taylor expansion. If this is close enough, we can use a Taylor expansion to calculate psi on this because we know that psi is constant on this, on the limit cycle. And you can do this, and it's not very hard because we said that psi is a solution of the Riccati equation, and actually psi of x near the point alpha was exactly x plus alpha squared divided by 2. So if you're at -1, you just have to plug it -1. And so this turned out to be exactly -1 plus alpha, or alpha -1 squared divided by 2 epsilon and a constant. Now this answers your question. If alpha if you are inside here, inside, we are back to what people have written for the last 30, 40 years. Mean first passage time is exponentially long. If it's exponentially long, you don't see the other eigenvalues in the expansion of the Fokker-Planck equation because they are completely hidden by this. Now what happened when you put alpha at a distance such that this is not anymore exponentially small, because 1 minus alpha can be of the order of epsilon if 1 minus alpha is sufficiently small. Now this is not anymore going to infinity as epsilon goes to 0. So this becomes of order 1, which we understood, because the mean first passage time is a time to escape, so you are going to be attracted here, and here obviously you are going to escape in a time of order 1. Now we need to calculate the rest of the spectrum to see how they contribute. So I have printed, it's not clear because it didn't print very well, but to show to you that what I'm telling you is correct. But this is the simulation where you see in red the accumulation and the peak. This is the peak. And this is the exit point on the circle. And now, you start to see the peaks, that the oscillation here, which is the contribution of the eigenfunction only in a certain range of 1 minus alpha. Before you don't see anything. And what I wanted to say is that so you see exactly from your dynamical system, you can see, now this is the stochastic simulation, not anymore the analysis, where you see in red, in green, the region of exit point. And you can see that indeed the trajectory are rotating before escape, and this corresponds to the peak in the distribution here of the exit time. So you have here this different peak that then are smeared into the first exponential decay. Okay, so this is the hard analysis. And we will continue next week for this one and to look at the spectrum. All right? Again, if you have any question, I'll be happy to go, if you want to go into the analysis in particular, to go step by step. But I think before going step by step, it's important to understand the principles. And we did 2 weeks, before we did carefully the case of the escape from an attractor. So from this, you'll have some information about how to do this.
It's very impressive. What I didn't follow.
Yes.
Is when alpha goes to 1, you have a singularity in this thing with when
this.
Yeah, when theta is minus pi.
Yeah.
But you're saying that there's this root epsilon.
Yes.
I don't understand what that should be.
This is a great question. So this is not captured by this analysis. This is because basically you neglect here some terms in epsilon, because you look at the leading order term.
Yeah, sure. Okay.
And this has been discovered in for radio, because when you have phase lock loop, people were tracking where you lose lock.
Yes.
And this is how they discover it.
Yeah.
And we started to realize this when we did the simulation, and you see you have to go, actually we have, let me show you in another, yeah. So this is when we looked at the different escape time distribution, and you see as epsilon is getting refined, this says, where is epsilon here? It's nowhere. But we could find as epsilon is getting smaller and smaller, that the distribution was shifted. So there is a shift, it converges to theta, and I know that it is of square root epsilon because of what they did in 30 years ago. So we haven't done the analysis here to show this, but we see it numerically. We looked at the distance at which points accumulate, and it goes like exactly square root epsilon. But it's not revealed here. So in the WKB, we have to go back and track terms of order 1. It's a small effect, but it can be, I mean, if you care about this, it can be important. Okay, so again, this is non-trivial asymptotics. It should go step by step to understand how it works. And why we did all of this. And next week we'll continue on this, and then the week after I'll start the narrow escape theory, how long it takes to escape through a small hole. And then we'll move on with basically some chemical reaction and maybe some class about aggregation for telomeres, which are the end of the chromosome. They can form cluster. So I want to discuss some models on this, which is important for understanding how, again, the nucleus in yeast is organized. Not all the cell nucleus, but yeast. They form cluster, and what can we say about the dynamic of cluster? But before we do the narrow escape problem, how long it takes for a particle to escape through a small hole.